You are here to learn how to use statistical methods to analyze research data. We're doing that, though fully understanding these methods sometimes requires a detour into a bit of theory or learning about a mathematical expression. This is one of those times. In this video, we'll take a brief stop to learn about the binomial coefficient. Once we have this learning in hand, we can move on to an important probability distribution that we will use in making inferences when we have dichotomous data. 3 students take an exam. Each student will earn a pass or a fail. The number of possible joint outcomes is 2 times 2 times 2 equals 8. Here are those 8 outcomes. Let's compare 2 of these possible outcomes, the second and the third. In this one, students 1 and 2 passed the exam, but student 3 failed the exam. In this next one, students 1 and 3 passed the exam, but student 2 failed the exam. If you were a researcher studying the pass rate of the exam, do you really care which 2 students pass and which one fails? Yes, the students themselves may care a great deal, but for you, as the researcher, both outcomes give you the same pass rate of 2 out of 3, or about 67%. The order does not matter. The question of interest is, how many joint outcomes include 2 students earning a pass and 1 student earning a fail? In this example, we can easily answer the question by counting. It is 3. Yet I wouldn't want to do this counting if there were 12 or 15 or 100 students taking the exam. That is where the binomial coefficient can help us. The binomial coefficient is based on the idea of permutations. A permutation of objects is a distinct ordering of these objects. The number of possible permutations of n objects is n factorial. We refer to this exclamation point as factorial. This is defined as n times n minus 1 times n minus 2 and so on, taking the product all the way down to a multiplication by 1. Also, by definition, 0 factorial is equal to 1. For example, 3 objects can be ordered 6 ways. Here's the formula to get there. 3 factorial is 3 times 2 times 1, which equals 6. Here's a picture to validate what we just calculated. This depicts all possible permutations of 3 objects. In our example of students taking the exam, we really don't need all permutations. We don't care whether the first and second students pass or the first and third students pass. In either case, 2 students pass. That is, we are dealing with permutations with identical objects. In this example, these objects, as it were, being pass and fail. If n objects are not all distinct, but instead include sets of identical objects, the number of permutations is given by this equation. N is the total number of objects, but n1 is the number of objects of the first type, n2 the number of objects of the second type, and so on, all the way to nk, the number of objects of the kth type. For example, 3 objects of 2 distinct types can be permuted 3 ways. In the numerator is 3 factorial because we have 3 objects. 2 of the objects are of the same type, so we have 2 factorial in the denominator. The third object is of another type, so we have 1 factorial also in the denominator. This results in 3 permutations. Here's the picture. Note that it doesn't matter which circle is which. They are both circles. This formula for calculating permutations with sets of objects is a bit easier when there are only two types of objects. It is known as the binomial coefficient. The binomial coefficient provides the number of unique permutations when n objects consist of two and only two types of objects. The notation on the left side of the equal sign is shorthand for binomial coefficient, and we describe it as n choose x. Look at the formula itself on the right-hand side of the equal sign. As before, n factorial is in the numerator. We have only two types of objects, x of one type and n minus x of the other type. Following the general formula, we have x factorial and n minus x factorial in the denominator. Let's look at an example. Here's the question we started with. How many joint outcomes include two students earning a pass and one student earning a fail? Note that the data are dichotomous and the events are Bernoulli events. Specifically, there are 3 Bernoulli events. The question is based on having two successes, so we will set x equal to 2. Then n minus x is 3 minus 2, or 1, which is the one failure. Let's use the binomial coefficient. This is 3 choose 2, so we have 3 factorial in the numerator, which is 3 times 2 times 1, or 6. We have 2 factorial in the denominator, which is 2 times 1, or 2. And we also have 3 minus 2 factorial, that is 1 factorial, in the denominator, and that's just 1. Doing the math gives us 6 over 2, or 3. There are 3 ways to have 2 passes and 1 failure with 3 students. We knew that would be the answer because we counted before, but it isn't always that easy. Here's another example that shows how we can use the binomial coefficient to eliminate some of the difficulties of counting. 10 students attempt a spatial reasoning task. How many permutations include 7 out of 10 students successfully completing the task in the allotted time? I don't want to draw all those permutations and count, so I'm going to use the binomial coefficient. We have 10 choose 7, which is 10 factorial divided by the product of 7 factorial and 3 factorial. This yields 120 different ways in which we can have 7 successes out of 10 trials. You have likely guessed, correctly so, that we don't even have to do this much by hand. Good statistical software will have a function for the binomial coefficient. It is okay to look at how this works and then walk away knowing that you can just use that function. The binomial coefficient can be used to calculate how many permutations there are of joint outcomes with a specific number of successes and failures when the response variable is dichotomous. Note that when statisticians use the terms success and failure with the binomial coefficient, they're not making value judgments. Rather, they are simply distinguishing among two events. It doesn't really matter which of the two outcomes you reference as the so-called success. Here is what is coming next that starts to move us towards using this in our research. If we know the number of permutations for every possible number of successes, we can construct a probability distribution for a dichotomous response variable. You know from your past experiences, primarily with the normal distribution, that once you have a probability distribution in hand, inference must be just around the corner.